All right, let's look at a little bit of the delta math when it comes down to this stuff. The graph of y equals f of x is a solid black graph right there. Which function represents the dotted graph? Now, what's cool about all this stuff is we can actually distill every single function into its parent function. We, depending on if we're adding or subtracting from our input before the function does its thing, or if we're adding or subtracting afterward. There are other types of transformations as well, but this is actually the graph f of x equals square root of x. That's what the black graph is right there. It's the same thing. Notice when x equals 9, y equals 3, because the square root of 9 is 3. When x equals 1, y equals 3, because the square root of 1 is, 1, because the square root of 1 is 1. So, all of this stuff is the exact same thing. So when I look at this thing, it doesn't matter what my function looks like. I just need to figure out how much it changed in the left and right direction and in the up and down direction. So I'm going to pick an easy to look at point. I feel like this is the most unique point right here. See, on both, I'm going to put it on both of the little graphs. I'm going to put it on the original and the resulting graph. And what I notice is the reason I chose that point to track is that it's going to help me count. I can count more easily because this is a unique point. I can easily look at it and see where it went. It's like the starting place is the black one and the ending place is the dotted line one. So I just need to count if it went left or right and how much, and if it went up and down and how much. So what I'm going to do first is I'm going to actually build my function right here. This was the original, so I'm just going to say it's y is equal to this. And I'm going to look at how much we went left to right. So it looks like to get from the point right here and its corresponding point right here, I had to go left 1, 2, 3. So if you add or if you move left or right, then you're going to change your input before the operation of the function ever happens, directly affecting your input x. So if we went left, that meant that no matter that every single input that we went to put in got something added to it to get it to be the same spot. So going left right here for transformations and translations is going to be a plus. And we went left 3, so it's going to be a plus 3 inside underneath this radical. And it looks like to get down to that, you had to go down 2. So outside of our radical, outside of the main operation of the function, we subtract 2 because it went down by 2. So it went left 3 and down 2. Those would be your transformations, your translations. So let's look at which one of these. So again, you can write this as the original function was f of x was square root of x. So you can write this as x plus 3, because our original function was f of x, and we added 3 to our input. That's why we went left by 3, and we went down by 2, so we subtracted 2 outside of the function. My alarm's going off. Both of my alarms are going off. That's terrible. I have no idea where my other phone is. Could have paused it, but it's okay. This is life. This is how it is. Anyway, so it is this one. But again, we can look at each one of these. This would mean going right by 3. So we don't have that. This would also mean going right by 3. So we are not going to use that one. This one would imply that we went up by 2. So the only one left is this one. Same idea here. We'll find the easy to identify point right here, and we'll correspond it with this point right here, and just count. So we went right, 1, 2, 3, 4. So if we went right by 4, then we have y equals square root of x was the original. Right by 4 is subtracting 4 before the operation happened. Going left and right directly adds or subtracts to the x value itself, inside of the operation of the function itself. And then it looks like we have to go down by 1. So outside of the operation, effectively modifying our output directly, we have to go down 1, so we subtract 1. So that's it itself. That's me creating it. But you can also just come down here and compare. This one would imply that it went left, so it's not that one. This one would also imply that it went left, so it's not that one. This one would imply that it went up, because this +1, so it's not that one. So the only one left is this one, and that is what I got. The graph y equals absolute value of x is the solid black graph below, which function represents the dotted graph. So I'm going to pick a unique point, because if I pick this one right here, it's hard to count where that went. But this is a unique point because it's easy to look at and figure out which way it went. So I like to start off with my left or right. It doesn't really matter to me. But it looks like to get from here to here, I have to go right by 2. So I had y is equal to absolute value of x. And I added 2. I went to the right 2, which means I subtract 2 right here. That means for every input value that I went to put in, I subtracted 2 before taking the absolute value. That's why it's going right. That's why it seems a little backward to you. And then I had to go up 1, 2, 3. So I get that. So that's it. Just counting. All of this is just counting. Keep the function as it is. And if you go left or right, you add or subtract, depending on which direction you went. If you go left, you're adding to your x. And if you go right, you're subtracting from your x. Same thing here. This is the vertex. I'm going to pick that one because that's the most unique point on our parabola. And it looks like it went over here. So we started off with y equals x squared. And I like to put some parentheses right here. Now, it looks like we just went left 1. So I'm going to add 1 inside of the parentheses before the square ever happened. You want those parentheses there because if you don't write those parentheses, you're just squaring that 1 or something. It looks weird and it doesn't work. So basically we have something squared. It was x squared, but since we moved left 1, it's going to be x plus 1 squared. Now we didn't move up or down, so we're not going to change that at all. But one thing to notice between the black graph and the dotted red graph is that it got reflected. The way we represent a reflection is just a negative outside of the function, multiplied onto the main part of the function, but outside of it. A -1 being multiplied on there reflects it. And again, the reason it does this is that no matter what you do for your input, when you get your output, it was looking like an upward-facing parabola, or a smiley face. But since we reflected it, when we multiply by a negative number, every single y value gets negated and becomes negative instead. That's why it gets reflected. But that's pretty much it right there.